Hello everyone, welcome back to Matematika class. So, this is our first chapter in the 12th grade for the Matematika Peminatan. Yeah, this is about limit. The last topic in limits that we haven't studied is trigonometric limit. So you can read it here. This is the competence. And let's start with doing the review for some trigonometric law and the law of limit first. Please match two equal terms. If x is an acute angle, you can pause and see whether your answer is correct or not. Yeah, so sin x plus 2 pi is sin x. Since it is in the first quadrant and sign is positive, sin minus x is minus sin x because it is in the fourth quadrant. And when it is a complementary relation, sign change become cos. Yeah. Okay, next. Please match again these two equal terms at the top and at the bottom. You can pause in here and let's see the answer later. Okay, so this is the answer for cos pi minus x. Since it is in the second quadrant, then it will be minus cos x. In here, it is still the same that x is an acute angle. Cos minus x. Since it is in the fourth quadrant, then cos is positive. So it is equal cos x. And for cos pi minus x, the same. If it is complementary, then it change become sine. Next, for the trigonometric graph, let's review. This is the graph of sine. This is the graph of cos. And this is the graph of tangent. And then here is the trigonometry review for the sum product formula. The first one, sine A plus sine B. 2 sine a half of the sum cos a half of the difference of the two angles. And also for sine minus sine, it will be 2 cos sine. Cos plus cos will be 2 cos cos. And cos minus cos will be minus 2 sine sine. All of these formulas having the same pattern. Yeah, please study it again. And last one is the trigonometry for the double angled formula. The first one, from cos 2x equal cos square x minus sine square x, we can change this formula become like this. Using identity and sine square change become cos square. So in here, we only have the term of cos. Cos 2x is 2 cos square x minus 1. Or what we will use in the limit later is how to change it become 2 cos square x. Yeah, cos 2x minus 1 is 2 cos square x. And the last form of cos 2x is 1 minus 2 sine square x, so that you can change it become like this. 2 sine square x equals 1 minus cos 2x. Okay, you can take a note for this relation because later we will use it in the limit trigonometry. Now for the limit review. Which of the following graphs has a limit value at A? Graph 1, graph 2, 3, 4, 5. Don't forget that limit exists if, what is it? The same approach from the left and from the right to one value. So you can pause and see whether your answer correct or not in the next slide. Here, the limit of fx approach A is exists at the first one in graph 3. You can check that the limit from the left and limit from the right goes to one value of L. And in here, you can check that this is donut in x equals A, that we can conclude that FA is undefined. Graph 4, the limit approach from left and approach from right showing you the same value, that is equals L. In here, FA is M. And at graph 5, you can see that the limit goes to the same value, which is also L, and in here FA is also L. So in these three graphs, the limit of fx is exists. How to solve trigonometric limits? Let's check. We have type 0, the same as the algebraic limit. When we have the direct substitution, this is the go-to method. You can use this and you use the other methods when this is fails. So first one, limits of sine theta. Since theta equal 0, sine theta is divine, then you can have the same value of the limit. Sine 0 is equal to 0. for limit theta approaching 0 of cos theta, also the same. You can just substitute cos 0 and the value is 1. And in here, please note that whenever you calculate the limit, the same as differential and integral, theta is always an angle in radian measure. So type 1 is indeterminate form, 0 over 0. You can check here, rewriting the limit in an equivalent form to change the form of the trigonometric terms, and so that you can calculate it. So the change of the form can be using factorization. You also can try to multiply with the conjugate or using the trigonometric identities. So after that, when this limit of trigonometrics change, you can evaluate the limits in its new form. So this is example 1 of the type 0. When you substitute limit of tangent theta, then the value is 0. What about limit of x times cos x when x approaching pi? Yeah, so in here you can separate the value and substitute it one by one. For the first limit, you can have the value of pi, and for the second term, you can have the value of cos pi, which is minus 1. So the value of limit x cos x is minus pi. Next, for the limit of x approaching 0 of sine square x, it will be limit of x approaching 0 of sine x, and later you can make the square, then the value is still 0, and the value is still 0. Example 2. If you see the indeterminate form, then this is an example for the fundamental theorem of the limit of trigonometry. This is the graph of y equals sine x over x. And as you can see it here, this is a hole or the donut in x approaching 0. So we will calculate what is the limit of x approaching 0 of sine x over x. For the function, since the division by 0 is not allowed, you can see that this function is undefined at x approaching 0. And from the graph, you can conclude that the limit is 1. Can you answer the reason why? Yeah, because from the left and from the right, it is approaching the same value, y equals 1. Okay, now we will discuss the squeeze theorem to prove the limit of sine x over x. First, we will make a circle, which is a unit circle with radius 1. This drawing and the animation can be opened at the GeoGebra later. Then we will prove that the value of the limit can be approached by using this squeeze theorem by this way. First of all, please check that we have the angle AOB is x radian. For the radian measure, 1 radian defined as the relation between the arc length AB compared to the radius. If the angle is 1, then AB or the arc length is equal to the radius r, which is also 1. So that if it is x radian, then in this sector we can have AB equal x, since the radius is 1. Next, please check the ratio between the triangle AOC. In this triangle, sine x, which is the opposite of her hypotenuse, is AC over 1. So since AO, which is the radius, is also 1, we can have AC is sine x. And for the bigger triangle DOB, tangent x here is BD over OB, opposite over adjacent. So since in this triangle OB, which is the radius, is 1, then we can have BD is tangent x. Next, by the diagram, it is obvious that sine x, which is the value of AC, is less than x, which is the arc length of AB, and less than BD, which is tangent x. So if we change tangent x become sine x over cos x, and we divide all terms here by sine x, then we can have this term become sine, x become x over sine, and sine over cos become 1 over cos. When x approaching 0, then we can see that the limit of 1 over cos x, you substitute x equals 0 and the value of cos 0 is 1, so that the value of this limit is also 1. Then, since at the left side it is the same with the value of 1, left and right, then using the squeeze theorem, we can also conclude that the limit of x over sine x is 1. If you make the reciprocal, then the limit of x approaching 0 of sine x over x will be also 1. So this is the fundamental limit theorem that is proved using the squeeze theorem. Since we have the basic for sine x over x, when x approaching 0 is 1, then you can later use it in any quantity denoted by x. As long as the argument of sine function and the denominator are equal, then, like this, for example, sine y over y is also 1, sine kx over kx is also 1, and sine fx over fx is 1 as well. Okay, that is for today. At the next meeting, we will continue the lesson to more examples available. Thank you everyone. Keep healthy and God bless you all. Bye bye.